Previously, we've taken a look at AC circuits that have either a resistor, an inductor, or a capacitor in them. Now I'd like to take a look at what if you have all three elements. Now to start, we're not going to have an AC EMF source. We'll just imagine that we've got a resistor, an inductor, and a capacitor, and we just imagine that you initially just put some charge on the capacitor and let things go. So we can say, look at this as the circuit is oscillating back and forth, just like it would have been without the resistor present. And we'll think about it at a moment when the current is flowing clockwise and we are putting positive charge on the upper plate of the capacitor. But the general result will be true. So we'll go ahead and write down Kirchhoff's loop law for this, so we can think about walking my imaginary dog around clockwise. So here I would be going with the current, so this will be minus IR. Here I'm going with the current, so this will be minus L di dt. Then here I'm leaving the capacitor on the negative side, so this is going to be a decrease in electric potential. So this will be minus Q over C, and then I get back home, I write equals 0. Now we recall that the rate at which the capacitor is charging is equal to the rate at which we're shoving charge on it, which will be the current. So we will note that the current is equal to dq dt. So if we go ahead and substitute that in, rearrange a little bit and multiply through by -1, you can rewrite this as, L d squared q dt squared plus r dq dt plus 1 over c times q equals 0. Now this particular differential equation is a real bear to solve, but it is doable. It's actually not that awful, but more than I want to do here. So I'll just go ahead and quote the result, and you are certainly welcome to stick the result back into the equation and see that it works. So we get that the charge as a function of time is whatever we initially charge the capacitor plates with times e to the minus RT over 2L times the cosine of omega prime t plus our initial phase, where omega prime is equal to omega squared minus r over 2L squared, and omega is 1 over root LC, which is the frequency that the circuit would want to oscillate at if the resistor weren't present. Now, for a lot of practical circuits, the values of R and L can be such that it doesn't change the resonant frequency very much from this. So a lot of times you can just get away with saying it's this, but you do have to be a little careful. Now, what I think will be an instructive activity is if you pause the video here and draw a graph of the charge on the capacitor plates as a function of time. So go ahead and do that, and when you're ready, go ahead and resume the video. All right, so when you plot it, it's going to look something like this. So this will be plus Q naught minus Q naught down here. So this is our charge. This is time. I'm going to draw a dotted line here. This dotted line is going to follow the function e to the minus RT over 2L. And we'll just do the matching one here that follows minus e to the minus RT over 2L. And then what we have in between is we sandwich in a cosine that goes in between in this envelope here. So what I would like you to do is ask yourself, have you seen a graph that looks like this before, back when you studied mechanics? So go ahead and pause the video and get back with me when you remember. Yeah, this is exactly what you saw when you looked at a damped harmonic oscillator. For instance, if you looked at a pendulum as it was swinging through the air and you saw how the amplitude decayed, it followed the exact same thing. And so this makes sense. The resistor is providing the electrical equivalent of drag here for our circuit. It's what's removing energy from it. All right, so now let's think instead about a case where we go ahead and insert an AC source into here. So again, R, L, there we go, C, like that. And we'll say that this source is going at some natural frequency that we'll call omega drive. And let's also just say that omega drive is unequal to the resonant frequency of the circuit, omega. Unequal. It could be, but we're not considering that right now. So let's say we're driving this at a frequency that's not the resonant frequency of the circuit. What frequency will the circuit oscillate at? What frequency will the current go at? Will it go at omega, the resonant frequency of the circuit, omega drive, the frequency at which the AC source is driving the circuit, or will it go at the average of those? So go ahead, pause the video, and get back with me. So again, just like with mechanical simple harmonic oscillators, it will go at the driving frequency, ignoring some transients at the very beginning. So it'll be our current here times cosine omega drive t. However, if the driving frequency is unequal to the resonant frequency of the circuit, there will be a phase difference. So the current will, although it'll oscillate at the same frequency as the EMF source, it will be out of phase with it. So a technique that we can use to find this phase difference is something called a phasor. Go ahead, get all of your Star Trek jokes out of your system now. So let's go and take a look at the EMF phasor as a quick example of how that works. So if we plot, if we plot the EMF as a function of time, it's a cosine, right? And so that should get us thinking about unit circle-y kinds of things here. This will correspond to a quarter of a period. this right here corresponds to half a period, 3/4 of a period, and a full period. And when we get to thinking about that, we think, wait a minute, this is just basically unit circle stuff. So what we can do is we can construct what's called a phasor. So here I'm just drawing an XY coordinate, if you will. And then what a phasor is just an arrow. This should not be confused with a vector, although they do some vector-like things, but this is not a vector. So this is our EMF phasor. Now what you imagine the phasor doing is you imagine that it's rotating around counterclockwise with angular frequency omega. So then at any given moment, the phase angle is this angle phi right here, and then this piece of it right here is the EMF at that exact moment. So what we do is we just imagine this arrow going around with angular frequency omega, and then we just take the x component of it and we plot the x component over here. Now, just as a quick heads up here, this is a physics phasor. With engineering phasors, they tend to do the projection off against the y-axis. That's just making a choice of sine versus cosine. Since we're using cosines here, we project off against the x-axis, but you get the same result. So we imagine the tails of these phasors are bolted onto the origin while the heads rotate around at our angular frequency. And I'll be going over the relative orientation of voltage and current phasors for different devices in the next little bit here. And then finally, to figure out the total phase of the circuit, it turns out that you can add phasors together like they're vectors. So we'll go ahead and flesh out some examples for that. So we'll start with what the phasors for resistors look like. So you remember that for a resistor, if we plotted both the voltage and the current, so we'll go ahead and plot the voltage in green again, like that. And we'll plot the current here, and I think I used purple before. There we go. They were always in sync with each other. So what this will correspond to when we draw phasors is I can go ahead and draw a voltage phasor. So this is the voltage phasor being for the voltage applied across the resistor. And it's then at the same time, if the voltage phasor is oriented like this, the current phasor has to be oriented the exact same way. And again, this phase angle here will be equal to omega t, and we imagine the whole thing rotating around with angular frequency omega. So as both of these spin around, their x coordinates will trace out nice cosine waves, and they will be in sync with each other. For capacitors, if you remember your friend Eli the Iceman, ice, I-C-E, C was for capacitor, the I came before the E, so it means the current leads the voltage. So for instance, if I were to plot against time here, Again, doing the same kind of plot. If my voltage, again, say looks something like that, my current will always be in front of the whatever the voltage phasor is doing by 90 degrees. So here it's coming to a peak 90 degrees early, like that. So when I plot the phasor like this, if this is my voltage phasor here, the current phasor will be in front of it. Sorry, that should be V sub C now. The current phasor will be in front of it by 90 degrees. Again, this is our phase angle here, and we imagine both phasors rotating, maintaining the 90-degree phase difference with angular velocity omega. So again, at any particular time, we can just pick off the x-coordinates, and they will correspond to the values of the voltage and the current. Now we can, just for a quick pause here, you can do the same kind of thing if you think about simple harmonic motion. So just to give you kind of an analogy here for a purely capacitive circuit, this would correspond to, say, a mass on a spring. If I plot the position we'll go ahead and make the position green just to keep the analogy going here. So if I plot the position like that, we know the velocity is equal to the derivative, so I'll go ahead and plot the velocity in purple here. There we go, something like that. I could, if I want, draw position and velocity phasors. So this would be my position phasor, so this would be of length A, our amplitude, and this would be our velocity phasor here, of length V max. And again, it would have a 90 degree difference, and you can say the whole thing's rotating with angular frequency omega. So just to show you, you can do the same thing with a mass on a spring. So you're not quite as useful most of the time, though. All right, and let's go ahead and finish this off by looking at an inductor. Again, if you remember our friend Eli the Iceman. You can go ahead and plot the voltage here. And remember, the L in Eli meant the inductor. So E came before I here, so this means the current lags by 90 degrees. So the current looks something like that, and the voltage looks like that. So if I were to express this with phasors, again here I can go ahead and draw a voltage phasor like so. And then my current phasor will be 90 degrees behind the voltage phasor. Again, this is my phase angle omega t, and the whole thing is rotating counterclockwise at angular frequency omega. So in the next video, we will go ahead and use this to analyze an RLC circuit. Catch you over there.